part, which is z cosine theta, and y is the vertical part, which is z sine theta. You learn this from complex numbers in level 1. Okay, now let's have a look at this. You see here, if we have V2, or let me say, this is the voltage V, okay, it is V2 sine omega t theta 2, and this is written in time domain, right? Before I start working into phasor, what I need to do, you see here sine, it should convert into cosine, so I can start converting to phasor. How can I do this? I will add here minus 90. Okay, the resultant will be this form, this equation. Now this equation in time domain could be converted into phasor domain. How? Have a look. I will call it V bold. The V bold means phasor. Maximum value, it will be come here, and the phase shift angle, this one, it will come here inside angle. Simple, right? This is the way how we represent phasor from time domain into phasor domain. Now let's also have some practice on phasor. So when we go to analyze electrical circuit in AC circuit, then we can deal with phasor easily. Have a look. If he told you to find the sum of V1 plus V2, and he gave you V1 in time domain here, see this is cosine, and there it's sine. You will say, okay, this one converted into 20 with an angle minus 45, as you can see here. And this is, by just a minute, this is sine. So here 60 minus 90, it will be minus 30. Okay, then it is 10 with minus 30. You see how I represented time into phasor? Okay. Now, can we add them directly? No, we cannot. You see here, this is polar representation. We cannot add polar. We need to convert into Cartesian. You remember polar and Cartesian? We need to convert from z and theta into x and y. Have a look. I will convert. This one, it will be x plus jy. So x is 20 cosine minus 45, and plus j, 20 sine minus 45. The same thing for this one, 10 cosine minus 30 plus j, 10 sine minus 30. Now we have here Cartesian. Next step is to add real with real, this one real with this one. Sorry. And this Cartesian, this is imaginary with imaginary. So we go to numbers. These are x and y. Now let's convert back into phasor, because we want the final to be in phasor phase, and then we convert into time domain. Now to convert this into phasor, what we will say, square root, because this one represents z, square root 22.8 square plus square 19.14 square. What about the angle? Angle will be tan inverse y over x. Y is minus 19.4 and x is 22.8. We got the angle. Now if I want to convert into time domain, then this is the maximum and this is the phase shift. I will say it is 29.77 cosine omega t minus 40.01. Please don't forget to write the units, okay? Volt. More example in conversion, okay? Have a look. This is Z10 with angle 60. This is polar or not? Yes, polar. Convert into Cartesian, 10 cosine angle plus j, 10 sine angle. Do the math. Now if another value Z2, this is polar, right? So convert to Cartesian, it will be 5 cosine the angle plus j sine the angle. Also do the math. Now if I want to multiply, yes, multiplication and division is easily in polar form. So we can, you see here, Z1 by Z2. I will multiply the magnitudes. These are the magnitudes, you see here. And add the angles, these angles to be added. 60 plus 45, it will be 105. What about division? Z over Z1 over Z2. Divide the magnitude, subtract the angle. 60 minus 45, it will be 15. You see? For addition, no, we cannot add polar. We need to convert into Cartesian and then add. How we add? Real with real. Example here, real with real, imaginary with imaginary. You see here? And the same thing for the second one. Now, reduce the following expression, this example, by using phasor. Have a look. This one, V1, is two parts, cosine and sine. For cosine, it's easy. 10, as you can see, with angle 0, because there is no phase shift here with omega t. But for this one, sine, it needs to convert into cosine. So we will add minus 90. It will be 10 with minus 90. If we want to add them, we need to convert into Cartesian and then do the math. You see here, this is the resultant in phasor. Returning back to time domain, then we will say that the maximum is 14.14, this one, cosine omega t minus 45, this is the angle. Okay, I will take one more example. Let me say the last one. Here you see 20 sine, it will be here. I need to add minus 90 because I need to convert into cosine. So what I will have 20 cosine omega t, because 90 minus 90 is 0. So it will be, as you can see here, 20 with angle 0. This is cosine directly, so it's 15 with angle minus 60. Can I add them directly? No, we cannot, because they are polar. So we need to convert into Cartesian and real with real, imaginary with imaginary. After that, back to phasor, then from phasor to time domain. So please, at home, try to do the calculation, work according to this example, take the experience in dealing with conversion from time domain to phasor domain, from phasor domain to time domain. Now, adding more example, adding sinusoids using phasor. You see, this is V1, which is 20 cosine omega t minus 45. It's ready. But this 10 sine, it is not ready. We need to add minus 90 to convert sine into cosine. Then this is how it looks like. Now, for this one, V1, it's 20 minus 45. You see, this is the magnitude, and this is the angle. For V2, this is the magnitude, and this is the angle. Okay. Now, if we want to convert 20 minus 45 back again, okay, back to from polar into Cartesian, we say that 20 cosine angle plus j 20 sine angle. Do the math. While V2, if I want to convert it from polar to Cartesian, I will say 10 cosine angle plus j 10 sine angle. Do the math. If we want to add, to find the resultant voltage, then we will add real with real, imaginary with imaginary. We got Vs equal these values. Then next I will convert into polar. So then I will say square root 2, the real part square plus the imaginary part square. We got 29.8. What about the angle? Tan inverse, theta will be tan inverse, real imaginary part minus, don't forget minus 19.14 over 22.8. We got the angle. Okay, now we can write the voltage in the resultant voltage in phasor, in polar, to be 29.8 with angle minus 40.09. If we want to convert into time domain, then this is the maximum, and the angle represents the phase angle or phase shift. Okay. Now it's like, just to make understanding how it look like this conversion. What we have is the voltage produced in the generator is sinusoidal, time domain, and this is it's rotating, or let me say fluctuating between plus and minus on the time axis, and this is synchronized with real and imaginary axis, because this one is rotating 360. You see, all let me say circulation is the same from 0, because here 90, 180 here, 270 here, and back here to 360. So one full cycle, which is equivalent in degree, equivalent to this in omega t, or time in second. Okay, and this is translated using, or let me say explained using Euler formula. Now more on phasor relationship, let's assume we have two voltages, V1 and V2. V1 is the 3 cosine omega t plus 90, 40, and I want to sketch this one. Just a minute. Plus 40, by the way, don't forget, when we rotate counterclockwise, anti-clockwise, it will be positive. Counterclockwise, it will be negative, right? It means rotating in this direction is positive, rotating in this direction is negative. Now, this is the 0. When he told me that there is phase shift 40, I need to search 40. Now I sketch the magnitude, which is the 3. What about this one? Minus. Minus, it means the opposite direction. How much from the 0 or the horizontal? 20. You see? Here, 20 degree. I sketch it, the arrow, okay, which is magnitude is 4. Right? Now, if I ask you, what is the phase shift of V1 with respect to 0, you will tell me this is 40. What is the phase shift between V2 with respect to 0? You will tell me it is 20. Now, if I ask you, what is the phase shift between V1 and V2? You will tell me it is 60 because you add both of them. Got it? Great. Now, example exercises. These are two exercises. I will not read them. I ask you, please try to practice. It is similar to the examples already discussed, but I want you to practice to get experience in dealing with phasor relationship. Okay. Now, in our AC circuits, we have R, we have L, we have C, resistance, inductance, capacitors, respectively. All of them are passive elements. Resistance consume energy, okay? Capacitance save or store electrical energy, and inductance store magnetic energy, okay? But all of them are passive. Now, what is the relationship for each one of them? Let's start in complex impedance. Okay, first of all, just let me remind you with resistance. What is the meaning of resistance physically? Physically, it is a physical property in any material. How much the resistivity of the material to the flow of electrical current. And we classify based on this into conductor, insulator, and semiconductor. Now, conductor conducting the electrical, insulator, as example copper, insulator is not conducting, as example porcelain. Okay. Now, this is in resistance. We call it resistance and represented by R. What is the effect of connecting inductance in the circuit? Okay. Or capacitance. It's also resists the flow of the current, but in a different way, rather than its real way, imaginary way. I will let you know what I mean by this. Have a look. Now we know that current will be Im sine omega t plus theta. Okay, this is how we represent the current. And the voltage across the inductance, we discussed this in week 1, that is LdI over dt. So if I differentiate this part, sine will be cosine, and we got this omega Lim. We can represent this by phasor Im, maximum current, theta, this is the voltage term, by the way, but I'm talking about the current. This is, okay, with phase shift is theta minus 90. Okay, now have a look from how we got this. Have a look. VL representing this VL here is omega Lim, which is the maximum here, with angle theta, right? Okay. Omega L, okay, omega L with angle 90, and IL represent this theta minus 90. I try to represent it here, define it here, and then substitute it here to make sure that there is 90 here, which is the phase shift of the impedance, okay, of the inductor. And then more simplification, it will be J omega L IL. Or in another way, we can write ZL is J omega L, which is omega L with angle 90. What does this tell me? This tells me that ZL, the impedance of the inductance, is on the imaginary part because of J, right? How much is value omega L? Do you remember omega? 2 pi f multiplied by L is give you, and this 90 to say that it is on the vertical axis. This is horizontal here, J. It's a plus J, okay? But at the end, VL equals ZL IL. This is the same Ohm's law in DC, okay? But this is in AC. V across the inductance equals ZL IL. Now, complex impedance, still with inductor, we represented VL equals ZL IL. Now, if I want to sketch it, I will see that if this is IL, this is VL, sorry, VM with angle theta, theta from here to here, okay? Which is the angle shift, phase shift between horizontal and the voltage, okay? When we sketch the current, we will find that the current delay by 90, okay, by 90 from the voltage. Voltage lead the current, or let me say current delay or lag the voltage. It's clear in this waveform in time domain, as you can see here, the black is the voltage, you see, and the current is the blue. You see, we reach the voltage before the current, okay? So 90 degree is the phase shift between voltage and current in a pure inductance, a pure imaginary inductance. This is called reactance. And now you have new terminology. You have resistance, you know it, okay? Reactance, which is represented usually by X, which is the like resistance but in AC for coming from inductance or capacitance. For inductance we call it XL, later on XC for capacitance. Now this is reactance. The general term for reactance, resistance, by the way, all of them in ohms, call the impedance. So impedance is the general name. It could be resistance alone, it could be inductance alone, it could be a mix of inductance and resistance. Okay. Now, for capacitor, VC, if we repeat the same discussion, we will find that VC again equals ZC IC, which is Ohm's law. Impedance multiplied by current give me the voltage. But how we calculate ZC? ZC is minus J 1 over omega C, or if we take minus J down, it will be positive J, or we can represent it here simply minus J represented as minus 90, right? Now, if I divide VC over ZC, you see here, Z is 1 over omega C, this is ZC, and the angle is minus 90. When I take it up, because subtraction here, theta minus 90, it will be plus 90. If I plotted, this is the voltage. Let's assume this is the angle theta. Okay? When we plot it, we will find that I will lead voltage, you see, by 90, because plus 90. What does this tell me? This tells me that, let's compare with inductance. In inductance, current lag the voltage by 90. But in capacitance, current lead the voltage by 90. What about resistance? The same DC, the same AC, which is Ohm's law. Okay, current and voltage, both of them in phase. There is no phase shift between them. They are in the same phase and have the same shape. You see, this is the voltage and this is the current, the same shape, the same phase. They started together at this point, they ended together at this point. Very easy. Okay, this is a practice exercise. You practice at home, please, on this. These are more exercises, number 2, 3, 4, 5. It's similar to the examples already discussed. Please try to do it. I want you to get the experience in dealing with this type of problems. See you in the next week to complete module number 1. Thank you.